I'm Professor Richard Harrison. I'm Chief Scientist at the Rutherford Appleton Laboratory in the Ralph Space Department. I'm a solar physicist by trade, although in my role here, I oversee the scientific areas, including lots of astronomical topics, solar physics, heliospheric physics, magnetospheric physics, and ionospheric physics. But a lot of that is to do with the sun and the space between the sun and the Earth and the impacts on the Earth. So that's really where I come in with the mission Solar Orbiter. And I've done a lot of research in the last large number of years into research on what happens in the sun's atmosphere and how it influences space and the space around us.
Yes, now the Solar Orbiter mission is really the reason that we're speaking today. And from what I believe, you were quite instrumental in the kind of foundation of the mission and kind of getting it to be approved.
I was actually involved, well, to go back to the beginning, I was a principal investigator on an instrument that was flown aboard the highly successful SOHO spacecraft, the Solar and Heliospheric Observatory, which is still going and was launched in 1995 by the European Space Agency mission working with NASA. And a few years after the launch of that mission, because it had been such a success and has been for a long period of time, ESA were really beginning to look for what was next, having really built a sort of reputation, if you like, in solar physics. And a few of us got together at ESTEC, which is the European Space Technology Centre in Holland, which is an ESA centre, to discuss what mission could follow. And we called a community meeting in 1998 in Tenerife, of all places, to get a large number of people together, really to debate what would be the next big solar physics mission. And of course, we've been looking at the sun from the Earth, from near the Earth, in other words, from within the ecliptic plane where all the planets are, if you like, forever. There are lots of things we hadn't done, in a sense. And what we were really looking for by the end of that mission, sorry, the end of that meeting, was to start thinking of an encounter mission. And you talk about encounter missions for the planets, and nobody really thinks about that twice now. You think, okay, if you want to study Mars, you go to Mars. You're not going to land on the sun, of course. That would be impossible. But you can fly closer to the sun, or pretty close to the sun, depending on what you want to do, and study the sun really close up and do physics that close to the sun you really can't do right out here where we are now. So that was the mandate, in effect, from that community, and a bunch of us proposed it to the European Space Agency panels in 2000, October 2000. We were presenting it to the panels, and it was selected. It took a long time before it's finally endorsed, and here we are a long time later looking for a launch next year.
Well, I mean, congratulations, first of all, because you can tell that these missions kind of, they aren't just kind of dreamed up at the drop of a hat, are they? It's kind of like, like a decade or two of proper research.
That's a very good point, actually, because there are a lot of people that think in terms of almost what you might think of as a Victorian scientist building something in his dining room or her dining room in 5 minutes. It's not like that. You spend years trying to define a mission. Then you end up working with industry, with the agency to define it thoroughly, to get to the point where you've gone through various phases and you can really start cutting metal, if you like. It's a long, drawn-out process. And then if it is an operation for as long as it is, say, for the SOHO spacecraft, over 2 decades, you're talking about a whole career.
Yeah, indeed. I mean, what stage is the Solar Orbiter at now?
Solar Orbiter, I mean, the instruments were delivered maybe a couple of years ago, something like that, and the whole lot has been integrated. We're onto the payload module, and the whole lot was mated up together. So you got the complete spacecraft, which has been tested in the last 6 months or so in Germany. The spacecraft was assembled in Stevenage in the UK with Airbus. But we got to the point within the last week where the spacecraft is now ready to go, ready to be shipped over to Cape Canaveral, ready for launch. And in effect, there was a celebration very recently of that impending event, as it were. So it goes over to the Cape, and we're heading towards a launch on February the 6th in next year. So it's getting close.
So once it actually launches, what is its journey to the sun going to be like?
Well, the journey to the sun is not quite like people might expect it to be. It's never a matter of just launching and you travel in a straight line. The way to do it is to make use of the fact that you can orbit things, if you like. Energetically, it's a sensible thing to do. So you want to end up in a solar orbit and use flybys of different planets to sort of kick you into the orbit that you want. They're like little sort of slingshot type things. You come close to a planet, it sort of flings you in a slightly different direction. Believe it or not, one of those flybys will be with the Earth. So it sort of comes back, which sounds really strange. Most of the flybys will be with Venus, which is closer to the sun than us, of course. And in doing that, ultimately, it will end up with an orbit that takes it closer to the sun than Mercury. So you'll end up something like 42 million kilometers from the sun, which sounds like a long way at the closest, but it's actually quite close enough. It's about as close as you can get instruments on a spacecraft to the sun that could actually look at the sun, if that makes any sense.
Yeah, I mean, that kind of brings me on to the next point, is that obviously the first thing you would think about is surely it's just going to melt. So what sort of kind of protective armors is the spaceship going to have?
Actually, in terms of the thermal side, it's good to sort of step back and point out there are two missions flying to the sun in encounter missions. One of them is called Parker Solar Probe, which is flying already. It was launched in August 2018, actually. And it's been orbiting the sun for a while. It flies past Venus as well. It's a very different orbit. Ultimately, it will get very, very close to the sun. If you looked at an image of the sun and thought of the size of a solar radius, if you like, it's only about 9 of those out from the sun. It almost goes through the outer atmosphere of the sun. But it's getting so close to the sun, it cannot possibly look at the sun. It's too close. But it can measure the particles and magnetic fields and things around the sun, the environment around the sun, if you like. And there's one instrument that looks out sideways, but you can't look at the sun. So it can make some useful measurements. What you really needed for that mission is another one working in concert with that mission a little bit further out that can actually look at the sun. So that's where the European one comes in, and the two will really work closely together. So Solar Orbiter is getting about as close as you can and still look at the sun. And both of them have, technically, I think you should call them dirty, great big heat shields on the front. I mean, the technology of those is phenomenal. And in the case of Solar Orbiter, you've got these little sort of peepholes, if you like. You can actually look through the heat shield, and clearly an awful lot of heat will still impact your instrument. If you didn't do anything, you'd be at something like 500 degrees, I believe, something of that sort of order. So you've got to have a thermal strategy, if you like. So it's not just a matter of having the heat shield out the front. You still want to look at the sun, so you get a load of extra heat in, not just the light that you want to use. So there are lots of different ways of coping with that, with radiator systems, techniques for sort of throwing excess heat out of the instrument, letting it go straight through, if you like, but saving the bits that you want to make the measurements and so on and so forth. So there's a whole spread of strategies within the different instruments to cope with that, being really, really well thought through.
When you say that the spacecraft will be able to actually look at the sun, does this mean that we'll be able to get kind of optical light images and kind of real close-up detail?
We will see, optical images, yes, perhaps not in the way that people think, because, and there are many sides to this. It's not just the optical side. We're getting up close and we can measure the environment around the sun in a way that we can't normally. So you're seeing the sort of outflow of material from the sun and the environment around the sun, and try to understand how does the sun drive that environment? Because ultimately that's the thing that sort of then propagates out as a solar wind and influences us. We live in that environment, if you like. So we're trying to work out how it forms, what it's all about. So you get instruments that are looking at that environment in situ at the spacecraft. They're not imaging the sun. They're just measuring around the spacecraft. The ones that are imaging the sun, though, tend to look a little bit alien, if you like, in that some of the instruments we've had on different spacecraft for years will use something that we call extreme ultraviolet light. So it's just like using your eyes, but sensitive to a different color, different wavelength, if you like, that your eyes can't see. The reason why we do that is the sun's atmosphere is really hot. You're talking about millions of degrees in the sun's atmosphere. And they're what we call plasmas. They're charged gases, basically. And all of those charged gases, those plasmas, are trapped in magnetic fields in the sun's atmosphere, which sounds all very abstract. But the sun has lots of weird magnetic fields. We live on a magnet at the Earth, of course, but it's very much like a bar magnet with a North Pole and a South Pole and so on and so forth. But the sun is a bit more complicated than that. The sun is basically a fluid object with magnetic fields generated because of the flows of these plasmas in the body of the sun. It has turbulence. It rotates in a very strange way. And you end up with lots of magnetic structures, which, again, sounds rather abstract, I know, but look at them like almost like elastic bands getting tied up in knots. And you see these plasmas actually in those magnetic loops, if you like, trapped on those elastic bands, if you want to look at it that way. So if you look at ultraviolet light, extreme ultraviolet light, you look at something that almost looks like a writhing plate of spaghetti. It's not like the smooth atmosphere or smooth surface that you see if you looked at the sun and you can see the odd sunspot or whatever. And of course, you shouldn't really look directly at the sun anyway. I've got to say that, of course, you shouldn't. But if you look in ultraviolet light, you get a very, very different picture. And that's telling you an awful lot about the physics of what's happening in the sun's atmosphere. Very complex, dynamic, dramatic place. And we use that ultraviolet light as well as visible light, as well as X-ray light, and a whole bunch of others that are being carried on with instruments carried on the spacecraft to study the physics of what's happening in that atmosphere close up. So yes, there'll be lots of nice high-resolution imaging, a lot of stuff that we've never really seen before. Think back to flying past Mars for the first time, or Mercury for the first time, or whatever, and there are things you're going to find that you didn't necessarily expect, or they'll be in greater detail.
Just while we're talking about the instruments, I think it's worth talking about the SPICE instrument, because isn't that an instrument that's actually being developed at RAL?
RAL was the place where the concept for the SPICE instrument actually started. At one point, it was actually, the same team were involved throughout, but at one point we thought in the UK we couldn't actually afford to build the instrument. So at one point it was actually moved out to the States as a US-led instrument with heavy UK involvement still, and then it came back again as a contract to ESA. So it was actually built here, but it's an international team as well that actually put the SPICE instrument together. The SPICE instrument comes out of instruments like the one we built for the Solar and Heliospheric Observatory, the SOHO spacecraft that I mentioned earlier. It's actually an extreme ultraviolet spectrometer, which again sounds a bit abstract, I know, but basically it's an instrument that can split up the light using a grating. So think of a visible light being split by a prism, but you're looking at the signatures of the ultraviolet light that are in that light that, oddly enough, in a sense, you can pick out characteristics in that light that can tell you what is in the sun's atmosphere, what's it made of, even how fast the plasmas are moving, how hot they are. When I say what it's made of, I'm meaning you can pick out trace elements of things like iron, magnesium, silicon, oxygen, the sort of things people might not be expecting, because the sun is mainly hydrogen with a little bit of helium. The rest is really all trace elements. It's basically the stuff we're made of, because we're all made out of the same cloud in the first place. But because those elements are there and those signatures are there, we can actually, well, it's almost a bit like doing like weather mapping of the sun's atmosphere. You can actually diagnose the plasmas, if you like. You can actually say, what's happening down there in terms of the physics. And that's really a useful tool to have. What we have in combination with that is there's an ultraviolet imager, which is led from Belgium, again with a heavy UK involvement, which actually will do the imaging at the same time. So the two working in concert will be great. Is
there, kind of beyond the sphere of solar physics, is there any kind of practical application for the knowledge that will be gained? For example, like protecting GPS systems on Earth and things like that?
Absolutely, there is. I always think of it as three reasons to study the sun in this way. One is you see processes that occur everywhere in the universe. So it's a way of studying the whole universe that we live in, if you like. And that means things like how are these plasmas accelerated or heated or whatever, explosions, flares, things like that, everything. The physics in those, we can learn an awful lot. And then that's sort of fundamental physics as well, if you like. It's not just what happens in space. You're learning processes in physics, if you like, using the sun as a way of studying physics. But the third thing really is the impact on us. You're right, in the sense that the sun does things that impact the Earth. In particular, the big worry, in a sense, is the clouds that erupt into space that we call coronal mass ejections, which is a dreadful name for anything. People have heard of flares, which are basically explosions in the sun's atmosphere, where these magnetic elastic band systems, as I started describing them before, these magnetic loops get tied up in knots, and basically there's a breakdown. Energy is dumped into the plasmas in the sun's atmosphere, and it's an explosion. In the case of a coronal mass ejection, it's slightly different. You, again, are building up energy in the sun's atmosphere, and the way that it releases the energy is a huge magnetic system just balloons out into space. And those can come crashing out through the solar system up to a couple of 1,000 kilometers per second. Tracking clouds like that is something we're just beginning to learn how to do with other spacecraft. We want to know what the impact is when they arrive at the Earth, and there are times when they arrive at the Earth, and there are. impacts on human systems. It can be things like power distribution systems, power blackouts or whatever, problems with communication systems, problems losing spacecraft, whatever. The energetic particles that can be accelerated ahead of these things you'd worry about for astronauts and so on, even high-flying, high-latitude aircraft, so on and so forth, and even the impact on the systems that give us our GPS signals and so on. So yes, this is effectively a price tag. We need to understand how the sun works and how it influences us. And Solar Orbiter is part of the process of learning the physics. There are other missions coming online really for the first time, in a sense, that really will be built to monitor things rather than do the physics. In other words, to sort of stand back and track these clouds coming out through space. A big one is the European Space Agency's Lagrange mission, which we've been proposing for quite a number of years, and developing the ideas to what we call a Phase A-B study. And hopefully, after the European Space Agency ministerial this year, we'll get the green light to go ahead and build basically a monitor that would be stationed well away from the Earth, looking back at the sun and the Earth at the same time. And that would all be built on the physics of what comes out of missions like Solar Orbiter.
I think it's really interesting thinking about the sun within our solar system in relation to things like the Apollo missions and the kind of missions to Mars. And I was kind of thinking about this today, and I was thinking missions to the sun and the sun itself in terms of kind of space flight and astronomy, it doesn't often get the same kudos, I don't think, as kind of say like the Apollo missions to the moon, which is obviously because we actually put human feet on the moon. But like, would you agree that there's maybe not as much attention paid to the sun as, say, Mars or Saturn or Jupiter, and that's quite ironic considering that nothing would exist without the sun?
It's funny. I know exactly what you mean. There are lots of answers to that, actually. I mean, the point is, when you talk to the public, everybody knows what the sun is. So when I give talks about the missions we're involved with, people can really relate to that, and they're very interested in that, and want to understand what it is that you see. And when you show them what the sun looks like, when this sort of plate of spaghetti movie that I was talking about earlier, or you show them the coronal mass ejections flying out and say, look, in the same picture as a little dot, and that's the Earth, and this cloud is flying over us, then people really do latch onto it. But I think you're right. It's not quite as romantic in a sense as flying to another planet and landing on another planet. But then you've got to look back and say, well, nobody's going to go to Mars until we have a far better understanding or system monitoring events like this so that people can be safe. In the days of the Apollo astronauts going to the moon, I mean, if you think of the space station now, for example, they're relatively well protected by the Earth's magnetic field. Going to the moon is a different matter. When the Apollo astronauts started going to the moon, we didn't really know that coronal mass ejections existed. They were discovered part of the way through the Apollo missions, and even then, I guess people didn't really realize what the impact might have been. And it's only since the Apollos that we actually realized that, I think it was between the last two, there was a big solar event, and if it had happened during either of the last two Apollo missions, it could have been disastrous. So there are worries. You sort of look back and think, oh, grief, we were lucky. But of course, if you don't know something exists, so you don't know how dangerous it is, what can you do?
I think that's what makes kind of missions like Solar Orbiter and indeed the Parker Solar Probe like really interesting from that perspective, just to see how, especially if we do get amazing images that will show us the sun in ways that we've never seen before, how that will kind of then translate into public awareness and people's appreciation for it.
I think that's absolutely true. I think I'd like to say on the SOHO mission I mentioned earlier, and some of the others have been flying since, there's a mission called Solar Dynamics Observatory that orbits the Earth. It's a NASA mission, has a lot of British cameras aboard, in fact, with truly high-resolution imaging from the Earth's, not the Earth's atmosphere, in the vicinity of the Earth, but orbiting the Earth. A lot of people have latched onto those. People do seem to get really interested in that. One example, actually, is a mission called Stereo, where Stereo actually does sit away from the Sun-Earth line and look back, basically, at the Sun and the Earth at the same time in the space between the two. And we're beginning to learn how to track these clouds, the coronal mass ejections, all the way from the Sun to the Earth, which we're still doing now, of course, as you'd imagine. And it was used as one of these public science things, where citizen science things, where people would get involved and actually participate in the tracking online. And a lot of people, and I mean thousands of people, really got involved with that. So I think actually it's catching up.
Brilliant, fantastic. Well, Richard, thanks very much for speaking to me today, and we'll look forward to the launch of Solar Orbiter in February, and also hopefully the decades of science that are yet to come.
It's a pleasure talking to you, and I look forward to that as well. Thank you.